Well, to create a new standard, it takes something that's not just a little bit different. It takes something that's really new.
I think one of the things that really separates us from the high primates is that we're tool builders. And that's what a computer is to me. It's the most remarkable tool that we've ever come up with. It's the equivalent of a bicycle for our minds.
Cloud can be a place where we can discover beautiful things. Thoreau said you're rich in proportion to what you can afford to let alone. You know, there's things we don't need to know. It's other people's job to handle them.
Ultimately, we're building out the equivalent of a global brain, you know, where all of the computers in the world, all the networks in the world are connected.
We take the grid, we take electricity for granted. We take the infrastructure that it should just be there, and so should computing. We want lots of innovation in the cloud, and open source and open standards give us that possibility.
Technology-free markets tend to produce more innovation because people can do things that everybody else thinks are crazy that turn out not to be crazy at all.
10, 9, 8, ignition sequence start. 5, 4, 3, 2, 1, 0. Launch commit, liftoff, we have liftoff.
60 years ago, Thomas Watson of IBM is reported to have said that he saw a need for no more than 5 computers worldwide. A dozen years ago, people said that only a few companies would need Google-scale computing infrastructure. We now know that they were all wrong.
I believe that democratizing large-scale computing could lead to the kind of game-changing advances in physics, chemistry, material sciences, and other fields.
History is a wave that moves through time slightly faster than we do, and we feel like we're up to date with technology, and then something wakes us up.
All right, it's my pleasure to welcome our first keynote speaker of the day to the stage. Our speaker is the former CTO of NASA. He's a pioneer in cloud computing. He's a founder of Nebula and the founder of OpenStack. So please give a warm round of applause for our first speaker, Chris Kemp.
Thank you. Great to be here. Cheers. Thank you. It's great to be here this morning. I've got a great talk to share with you this morning. I'm going to tell you a little bit about the story of OpenStack and how it emerged out of a small team at an otherwise very large and bureaucratic organization. And I'm hoping that one of you or a team here will do the same thing in healthcare that we did for computing inside NASA. So when I first started thinking about space, I was a very young child. Actually, I had this photo, and I didn't really understand the significance of it as a kid, but this photo was called Earthrise. And it actually has a lot of symbolic significance for me because this photo wasn't meant to be taken. This was taken December 24th, Christmas Eve of 1968, by an astronaut named Bill Anders aboard the Apollo 8 spacecraft. And it was kind of a joking exchange between Houston and the spacecraft where they said, hey, don't take that photo, it's not scheduled to be taken. And sometimes things that you don't plan to do become really important. And this photograph actually became one of the most important photographs ever taken. In the 1960s, this became one of the symbols of this movement to think about the Earth as a fragile place that we have to preserve. And the environmental movement was really rooted in this new view of our planet as this fragile thing floating out in the middle of the solar system. So when I was given the opportunity to join NASA, we were doing some really cool stuff on Mars. And we had just launched a spacecraft called the Mars Reconnaissance Orbiter. And that had an instrument that was mapping the surface in high resolution, very similar to how Google maps the planet. You can kind of zoom in and see your house. We were doing the same thing for Mars because we're trying to figure out where to put a rover. And we wanted to understand the best place to put it. So we had these giant massive data files that you could download from JPL. And I think they were like 600 megabytes. And here in Kansas City with Google Fiber, I know that would take about 10 seconds, but where I live in Silicon Valley, I mean, that's like at least a 20-minute download. Comcast. So obviously, NASA was complying with the idea that we wanted to share all this information. But the idea that in order to really see it, you had to download a 600 megabyte JPEG file wasn't really, I mean, it was kind of the complying with the letter of the law, but not the spirit of the law, so to speak. Not that it was a law that they had to share it. But the idea that you could view Mars in much the same way that you view Earth really inspired me. And so I worked on a partnership with Google where we had a team from NASA work with Google to take all of this imagery and actually make a little Mars button in Google Earth. And about 1 billion people have downloaded Google Earth across the world. And so the idea was we could make it really easy for people to see what NASA was up to. And we ended up creating a Moon and a Mars button so you could actually see all of the data that's ever been collected from all of our missions. You can see photographs taken by the various rovers we have out there. This is actually Victoria Crater. It's a massive crater. We've actually had rovers circle around the edges of it, and you can actually go into Google Earth and you can view this in 3D. You can fly through it. It's very cool. As a public agency, as a government employee, I didn't want to just do stuff with Google, right? We wanted to reach out to all the companies in Silicon Valley. So the challenge was, when we started working with other companies, they didn't have Google's vast infrastructure to host all this data. So we had to solve this problem, which was we wanted to have the cost structure of Google inside NASA. And the problem with that is it was very expensive to operate IT infrastructure. Whenever we bought servers and managed data centers, there was a huge cost associated with procuring and racking and stacking and operating and powering and cooling and all these infrastructures, which is kind of ironic given NASA's history in computing. Some of the first large-scale computing systems were built at NASA. The first microprocessors were used on Apollo. I at the time was promoted into a CIO role. So I was the CIO of one of NASA's research centers called Ames, which is in the background of this photo. And we had multiple power substations. We operated one of the DNS root servers. We had multiple connections. We had a facility called Mae West, which back when the internet had 7 physical nodes was one of them. And so we had some of the best connectivity on the planet. Does not extend into our living rooms like it does here, but we had this amazing capability which was not being tapped. So what I wanted to do was essentially just take a book out of what Facebook and Google and Amazon were doing with their infrastructure and replicate that inside NASA. And so the idea was we put computing in shipping containers. So we'd buy these large shipping containers, fill them with servers. People don't like working in shipping containers. So that kind of solved the problem of having too many systems administrators in the data center, because if the data center was parked in a field somewhere, it would kind of force you to remotely manage it. So we built this thing, we called it Nebula, the NASA Nebula project. And this was back in 2008 and 2009 when I was CIO out there. And as it turned out, the government, which is one of the largest organizations in the world in terms of its IT footprint, they spend almost $90 billion a year on IT alone. And that's across all the federal, non-classified federal agencies. And we were looking at the opportunity to take cloud computing and turn it into a major strategic cost savings and agility initiative in the federal government. And so the White House appointed a guy named Vivek Kundra as the first CIO of the United States of America. And Vivek was looking at what we were doing out at NASA with this Nebula project and said, hey, this is a really interesting approach. Let's launch our cloud computing strategy out in Silicon Valley. So the White House sent this delegation out to Silicon Valley, which was great because the idea that data centers weren't rooms full of people was not popular, right? From a lot of government agencies are really, that's code for jobs programs in a lot of states. And so when your position is you should have all your infrastructure operate without people, and we should be able to do this like big internet companies do this, this was somewhat unpopular, so we were getting a lot of congressional interest, shall we say, in the project that we had launched, and the White House coming out and saying, hey, this is how we should be doing things, really is the ultimate clearing the way for what our team was trying to do. So when you try to do cloud computing in an organization that's used to doing something one way, we're going to talk a little bit about what that means, you tend to have resistance. And in my case, it was Congress, and the White House had to step in. That's how far it had to go in order to do something really innovative like this inside the government. And we ultimately ended up hosting one of the very first websites that the president worked on in his political career, a website called usaspending.gov. And on the NASA Nebula infrastructure, we were hosting this website that would provide high level of granular visibility into every dollar of a $4 trillion budget. And so you can literally go to this website and drill down, and you can see every project, every agency, every government contractor in every district, and how that's all, you can slice and dice and visualize the data in all these different ways. And we needed to do this quickly, in months, and we needed to do it on a budget which was measured in hundreds of thousands of dollars and not hundreds of millions of dollars, which you might otherwise associate with a large government website program that doesn't work very well. The thing that we did next was a bit surprising. We decided we would open source all of the technology that we used to build this stuff. And we open sourced it under an Apache license. And for those of you that are privy to open source software, what this meant was anybody can do anything with this technology. You can fork it, you can commercialize it. Unlike viral licenses where you're forced to distribute your code and you have a lot of constraints around what you can do with the technology, we kind of pioneered this in the government. Usually the government used its own internal licensing formats. We had something called NOSA, which was a NASA open source agreement framework. No one knew how to work with it. And so when we open sourced everything, we were very interested in making sure that we had a broad community of support around the project. And open source is a really interesting way to disrupt a market. What emerged out of this is a project called OpenStack. And OpenStack, at first, we partnered up with an organization called Rackspace Hosting, which is a data center hosting company. And when we first announced this, which was only about 4 years ago in OSCON up in Portland, we had two projects. The NASA team contributed a project called Nova, which was the core technology in the NASA Nebula program, and Swift, which is an object storage technology, which is similar to Amazon's S3 object store. So it's essentially a storage technology that does not present a file system or a native block storage device, but just a way to write objects, essentially through RESTful web services, cover them. And in 2010, these two projects launched OpenStack. Today, there are 7 projects. This project has now expanded to include basic infrastructure services, security and identity services. This year, we're adding complete compute, network, and storage abstractions. So essentially what this is this is an open source Amazon Web Services. So if you want to operate your own cloud, this is very similar. The way I like to think of it is what Linux is to a workstation or a computer, OpenStack is to a data center. And so if you want to treat an entire data center as one system, this is a software framework that you can use to build your own data center cloud computer. In 2015, we're going to see additional projects added to this. And why this is all happening is OpenStack has been a very successful open source project. If you look at Linux, it took Linus Torvalds 3 or 4 years before he was getting his first sponsorships and was getting out of his dorm room. OpenStack already has 15,000 members. In terms of developers actively contributing code, this project in the last 3 years has gone from a dozen to over 750 individuals that are actually contributing code, which is being absorbed into the open source project on a 30-day rolling period. The Developer Summit, which we just got back from in Atlanta 2 weeks ago, had 5,000 people in a room like this, about twice as deep. And that's doubled every year since the inception. So we had 20 people, then we had it more than doubled, but it's been going from 5,000, 2,500, 1,200 every year. And this is an interesting graph. This shows OpenStack in people's job descriptions over time. OpenStack's the orange line, Amazon and some other stuff is in the other line. So you can kind of see there's a huge demand. HP is hiring 3,000 developers to work on OpenStack. Cisco and IBM have both announced they're investing $1 billion in migrating all of their internal infrastructure to OpenStack. Large service providers like AT&T are using OpenStack to host hundreds of applications today. So it's been a pretty impressive project to go from not existing 4 years ago to powering some of the world's largest companies and infrastructures. And so the question is, why did that happen? That's kind of not normal. Those are actually the logos of some of the core companies behind OpenStack today. eBay's using it extensively, PayPal, just to name a few. What's happening is a confluence of things, and I think this will have a huge impact on the healthcare industry. If you look at the amount of data which is being stored, it is increasing exponentially, and the numbers are staggering. So if you think about, and these numbers were just updated, and it continues on. If you go to kpcb.com/internet trends, these are a subset of 150 slides, which a former Morgan Stanley analyst pulls together from various companies. 4 trillion gigabytes is a number which is unfathomable. I mean, I don't even know how to consider that. So to put it in real human terms, these 4 websites every day store over 500 million photographs. That's something that I think everybody in the room can kind of grok. So if you think about that, and this number is now even higher. So if you look at Snapchat, Snapchat is now exceeding Facebook in terms of the number of photographs, which we now know they're storing. So if you look at these numbers, I mean, what do you do with 500 million photographs? I guarantee you don't put it on an enterprise storage array. It's not even sufficient anymore to take hard disks that are 4 or 6 terabytes or 8 terabytes and buy them in volume from hard disk manufacturers and put them in trays. I mean, we're having to even get more creative. And so there's a whole new generation of companies that are launching that are using flash technologies, spinning disk technologies, holographic technologies to address this problem. Because there's this expectation that you can just take all these photographs and they'll synchronize across all of your devices and then never go away. Sometimes we want them to go away. And it's not just photographs, it's videos. So if you look at YouTube alone, over 100 hours of video are uploaded every minute. If you look at some relevant to this community, API calls to MyFitnessPal, which is a website that aggregates devices that collect telemetry from our various sensors that we're able to buy now and place all around ourselves. This is growing exponentially, and this will only continue to grow as Apple obviously announced HealthBook earlier this week. The new Samsung Galaxy S5, which came out before these numbers came out, has various biometric sensors, including heart rate monitors. There will be more and more sensors in more and more devices, allowing us to collect more and more information, creating a problem with, creating all sorts of opportunities, I should say, where you can take all this information, correlate it to other information, creating a demand for both compute and storage. What's also interesting is this is increasingly mobile. So where we saw a lot of fixed computers in people's houses generating most of the traffic, we're now starting to see an increasing amount of traffic become mobile. So increasingly, it's our phones and our tablets that are generating all this data and traffic on the internet. So this is a global internet traffic over time. We're starting to see a trend line. I believe it's now up to about 25% in 2014 with the latest numbers. Almost 20% of all global internet traffic originates from a phone. And this is perhaps the most interesting stat. And I'm going to tie all this back together here in a second. This is the most interesting one that changed the most in the latest numbers, which I just read over last night, we have tablets, notebooks, and PCs since 1995. And you can see the personal computer dominated the computer industry. We saw back in 2008, 2009, the laptop really start to become the dominant thing that people bought. Out of nowhere, in 2011, tablets hit the scene. And now we're starting to see, and in fact, this last year, tablets surpassed PC and laptop sales. And the impact that this is having isn't just on us individually as consumers of information, as people that interact with our healthcare providers, our governments, the companies that we interact with, our friends that we interact with through these social networks, but it's pervasive. It affects the entire computing ecosystem. So the personal computer, okay, that's not really fair. Okay, the personal computer isn't really the focal point of computing anymore. Everything that you know about computing, in enterprise computing, networks, hard disks, memory chips, it's all derived from what people are manufacturing in factories. It's about the volume production of components. And today, what's happening is the computer industry is largely gravitating towards mobile devices that integrate with hyperscale computing environments. This is driving the volume in the computer industry today. So if you're buying servers that have hard disks and kind of do things the way that you've been doing them for the past 10 or 15 years, we're well beyond the point where that is no longer relevant. It's certainly no longer relevant to Facebook. It's certainly no longer relevant to any large internet company. If you're going to be dealing with petabytes, exabytes, zettabytes of information, it is no longer relevant. What is relevant is hyperscale computing and what's happening in the mobile scene. And this is great because they kind of go together. The opportunity to re-architect your applications for a mobile experience is a great time to embrace hyperscale computing architectures, scale-out computing architectures. The real problem is we've reached a point where you can no longer scale up, when a file system can no longer get any bigger because of physics. And so we actually have to impact the architecture of software, where software has to accommodate the global distribution of data. And people have written books on this stuff, right? Cap theorem talks about how you cannot have global consistency, availability, and performance at the same time. You have to pick two. And the problem is we've been able to scale up until this point, but you can't scale up anymore if you're dealing with 500 million photos every day. You can't put that on POSIX file system anymore. You have to figure out other ways to store data. And so we're starting to see a whole new spectrum of computing. And we're starting to see, and this will only further exacerbate the problem. As computers get cheaper and cheaper, as the ability with a low-power Bluetooth device to monitor your health telemetry and then beam that up to an internet service becomes cheaper and cheaper, which it will, this spectrum of computing will mean that we're being pushed out to the edges. Increasingly, your customers, the consumers, will have these less and less expensive, your cars, for example. I live in Mountain View where I literally pass about 10 Google self-driving cars a day. Stuff's real, right? They're all over the place. And they generate gigabytes of data every second. And that's interesting. It's not data you just throw out. I mean, it's definitely useful as the cars drive themselves, but it's also useful for insurance companies that are trying to figure out how safe these things are. And if something does happen, to mitigate risk and address liability issues. So I think what we're seeing is big companies increasingly pressured to spend hundreds of millions or billions of dollars on infrastructure so that they can deal with hundreds of millions of consumers that are literally using tens of inexpensive devices in their daily lives, generating more data, which is part of this ecosystem. And healthcare is going to be very interesting. So the question is, what does this all have to do with you all and cloud computing? Try that back. Let me go back, actually. So the problem is we're kind of in this juxtaposition where a lot of enterprises are optimizing what I'll call zero impact to software. And there are technologies like VMware that make this very easy to do. Virtualization is essentially a holodeck for software. So the idea is if you can run your software like it's 1995 in the year 2025, why not, right? So you can upgrade generations of infrastructure and the software doesn't even know, right? And as VMware virtualizes more, you get trapped more and more in that paradigm of static computing. So if you can virtualize the network doesn't need to change. You don't have to worry about IPv6. If you can virtualize storage, you don't have to worry about the high availability of storage because that's abstracted away. Virtualizing computing, it's a very convenient way to deal with 25 years of software. However, when you start to think about dealing with hundreds of millions of photographs and crunching data in real time and stream processing of data, the technology is useless. Not a single internet company uses this technology. Not a single one. Not a single startup that builds a new product, whether it be Uber, whether it be Airbnb. Nothing you use in your consumer lives uses any of this enterprise technology. Most of these technologies are built natively on cloud, using cloud service providers, and the companies that scale beyond that never use enterprise storage, enterprise networking, or enterprise virtualization. Just not useful. Now, if you look at what the big internet companies have done, they've literally invested billions of dollars in what you all do, which is in applications that can run on hyperscale infrastructure, because they realize that the value is in software. And if we're going to continue to generate more information, and winning is being able to store more information and make more use out of that information and provide more value for consumers, then your ability to operate that infrastructure efficiently is key to your success. It's key to your survival, in fact. And so if you look at what Google and the internet companies have done, is they have optimized for extreme operational and hardware efficiency. If you look at what Google and Facebook pay for a server, it's hundreds of dollars, and it's low. It's single-digit hundreds of dollars. It's not thousands or tens of thousands of dollars like you likely pay here. And if a server only costs a few $100s, you're not buying support contracts. You don't even care if it breaks. So we're really talking about an opposite paradigm, where instead of trying to take a very expensive overbuilt server that never fails and then running 100 things on it, which is what virtualization does, it's taking one server and turning it into 10. We're talking about taking 10 or 100 or 100,000 servers and turning it back into one. And so literally OpenStack is the opposite of virtualization. It's taking an entire data center and treating it as a single server for a single application. And if you look at that paradigm, cloud computing, one of the proudest things I've ever done in the government. I served on a healthcare subcommittee thing. It was terrible. But this was great work. So this was NIST defining what cloud computing was. And there's a URL down there, but if you Google NIST cloud definition, this is a 1.5 page document. I should work for the IRS, that describes what cloud computing is, and it's brilliant. Because this definition is self-reinforcing, and if you take any of these things away, it all falls apart. So if you take computing and you make it on-demand, elastic, shared, metered, and accessible, and you just stop making it shared, then you have a dedicated system. And so all the economics break down. If you don't meter it, if you don't have an economic incentive for an application to shut down infrastructure resources, well, don't, right? And so it becomes infinitely expensive. And so what's great about this definition is if you're not doing all these things from the perspective of the end user or the application, you won't have any of the benefits of cloud computing. You, like an internet company, won't have the agility, you won't have the efficiency in that infrastructure and you can subsidize it here at a big company. You can't subsidize it at a startup. And I think that's one of the biggest paradigm shifts. If you think about a new application, you shouldn't be paying for any infrastructure when no one's using it. You should be able to, on the other hand of that, you should be able to take an entire production infrastructure, simulate it for 15 minutes, and then tear it down. And it should operate, and you should be able to test it at the scale of your production application. But it won't cost you very much, because you only had it running for 15 minutes. And that's kind of how we think about cloud computing. And the challenge is, this is diametrically opposed to the way you think about computing. So if you think about infrastructure before and after cloud, right now you're dealing with on approval, static, private, purchased, and inaccessible infrastructure, fundamentally. And this is how applications required you to think about the problem. Security is all about creating a system boundary. It's about creating a security plan. It's about isolating those physical resources. And the challenge is, moving into this cloud paradigm, you have to really consider this very differently. And perhaps the best way to think about this is in terms of security, scalability, reliability, and data gravity. Economics also play a role, but I couldn't fit it into this little graph. Made it all three-dimensional and stuff. So if you think about security, you start to think about controls. You don't think about more or less secure when you think about cloud, because that's somewhat arbitrary. So if you think about fewer controls, you're delegating controls, say to Amazon. You're trusting that Amazon will do what they say they'll do if you use Amazon. And that's not a bad thing, because it might be more efficient for them to do those things. But that's what you're doing. And in some cases, other governments might not trust Amazon because they don't trust our government. And so you start to deal with these issues of trust. But it is really all about how much control do you want over the physical infrastructure and the services that you're building your stuff on. If you think about data gravity, we're starting to see a whole new generation of gene sequencers. It's a huge market for us, where these sequencers are each able to produce many terabytes of data. Moving this data up to the cloud, unless you're here in Kansas City and have Google Fiber, which no one else does, is nearly impossible, right? And so if you have a whole battery of gene sequencers moving tens or hundreds of terabytes of data up to Amazon's data center, you can't sequence fast enough. You can't move the data fast enough. And we don't see that changing in the next few years. So if you operate infrastructure, that's an important factor. In terms of, perhaps the most important thing is, and that kind of moves you right or left, from public clouds and managed services to private clouds and doing things in your own infrastructure. When you move up and down on this graph from the perspective of an application, you deal with scalability and reliability. If making an application reliable, you are relying on the underlying infrastructure. So if a server fails, if a network fails, if a disk fails, a disk subsystem fails, your application breaks, you should not run that in cloud, right? Because the assumption in cloud is that any of the pieces of infrastructure could fail at any moment. So you're designing for failure. And this is where the economics come from. If you're able to buy a several $100 server instead of something that costs 2 orders of magnitude more, but design your application so that it operates in the event of one server or even a rack or even an entire data center failing, then you don't care about data center availability anymore. You don't care about generators. You don't care about support contracts. The entire cost structure of your data center changes. And now you can operate lights-out data centers, like Facebook does, next to hydroelectric power plants with a handful of employees. And your ratio of employees to servers goes from a couple for every 100 servers to a couple for every couple of thousand servers. And your cost structure for those servers decreases, and the storage decreases as well. But the key is you've got to move the reliability away from the infrastructure into the application. And so what we're seeing storage technologies that do this. Object store. An object store, quite simply, writes 3 copies of an object into 3 different places. You could write more. And so what that means is if a disk fails, you're fine. If a rack fails, you're fine. If a data center fails, you're fine, as long as you put a copy in 3 different places. And the statistical probability that all 3 of those things happen is about 16 nines of reliability if you do it right. And so you're actually having more, but the problem is most applications don't like you writing data to an object store. They like writing data to a file system, right? And so if you depend on the semantics of a block storage device or a file system, you have to touch the application. Your application has to be aware that it's writing data to an object store and not a block store. And that's the problem. And so we've gotten sucked into really exotic technologies like Fusion I/O, solid-state storage technologies, very fast enterprise storage arrays, because we've had to scale up. We've had to make a database go faster. There's 2 ways to make the database go faster, right? You can scale up, or you can scale out. And so we've already seen scaling up take us as far as we can go. There's a whole generation of what we call partitioning technologies, like Greenplum, where you can take pieces of your data, put them here. So say you had a petabyte of data and you had A through C here, D B through G here, and so forth. That gets you so far, but you still have this bottleneck of a single point, this application which can only scale so much. What we're seeing now is scale-out architectures. You take entire application stacks and you create multiple copies of them, and you actually develop your application for eventual consistency. Most applications are just fine with eventual consistency. The only ones that are not are typically financial institutions where you actually really rely on, and financial transactions where you rely on instantaneous global consistency of data. When I upload a picture to Facebook, in Europe, it might take a few minutes before someone sees it, and that's okay. The application doesn't crash. And that's the key to building applications in this world. One of my favorite people is Adrian Cockcroft, and he was the chief cloud architect at Netflix until recently. Good guy to have come out here next year. He led the effort at Netflix to build all of their infrastructure on Amazon. And made lots of slides, but this is the only one that I really think is relevant today, which is that every single piece of your application is touched by running it on cloud. You can no longer rely on a central database. Because what happens if it fails? What happens if a continent goes down? You've got to take a distributed approach to storing data. You no longer can use application servers where you have session data in memory, because if that goes away, everybody's impacted. So you've got to take copies of your session and scale it out to hundreds of, or at least tens of different devices that can replicate in real time. Chatty protocols break the system, right? Because if you have applications running across multiple data centers in multiple regions of the world, too much chattiness in your protocol will slow it down. Will slow the application down so that it doesn't work. We've moved away from instrumenting code. How many of you instrument code? Right? Moving to cloud means instrumenting services. It means looking at the health of and the reliability of services and making stacks of services. So I guess the point here is that there's an opportunity in every single aspect of the application stack to do things differently, and in fact a requirement to do things differently. And unfortunately, what I'm laying out here, if you looked at every application Cerner produces and think about re-architecting it to run on Amazon reliably, that's a 10-year project. And your competitors are looking at this as well, and they're going to make a decision on when they start to make that investment. And if they make that investment and their core technology scales out on servers that cost hundreds of dollars, and they're able to take petabytes of data and drive value for their customers for that, they win. And that's the challenge here. And so a lot of times, it's hard to make this investment because it really requires thinking very differently about the architecture. And the assumption here is that data is going to matter and that you're going to collect more and more data and that that's going to be strategic to you. If that's not the case, you don't need to do any of this stuff because the computers will get faster and they'll easily run the system that you've already built. The software of today will have no problem running on Intel's processors of tomorrow. The good news is a lot of the technology that the internet companies have built that does this has been open sourced and is available for free today. So if you look at technologies like Hadoop, this is a distributed data analysis framework that does exactly what we talked about. It takes the data, leaves it where it is, and then it allows you to process and reduce and map these data sets where they sit. But it requires a different way of thinking about computing. To kind of drill into that, when I first started Nebula, there was a researcher named Jim Gray. And got to do a lot of really fun stuff at NASA, but one of the most, it was one of the most personally challenging things that I got sucked into was, Jim was one of the guys who kind of wrote the book on distributed computing. He's published a number of ACM papers, which are freely downloadable, that talk about how you have to think about computing in terms of economics. I highly recommend you read them because they're very good. But the basic principles that he liked to talk about are, look, if it takes a certain amount of time to compute something, or if it takes a certain amount of time to move a piece of information between one place and another in an application, or if it costs a certain amount of money to store a piece of information on a disk, you start to think about the architecture of your application from an economic perspective, especially at scale. And it just doesn't make any sense For example, if you have many petabytes of data, to put all that data on a disk system, especially if you want to query it in real time, move it across a network, a storage network, to a bunch of compute nodes, because the architecture is fundamentally slow. And if you look at, if you could build your application so that it can run on the nodes where the data sits, the aggregate performance of 1,000 servers with direct attached disks will always be higher than the fastest dedicated storage appliance, right? So if you can take, if your application is designed to take advantage of the ability to run code on a box with disks attached to it, you've got the native performance of reading off those disks on that node. So if you build your application that way, and that's not how Oracle works, right? Oracle puts all your data in a big database on a storage system, and then you're reading and writing to it from what is fundamentally a scale-up system. The point is that the other approach is both exponentially cheaper, it's also exponentially faster, and it can also be exponentially more reliable. It's just pain because you have to rewrite the application. But since you guys write applications here, you're the people to solve this, right? It won't be hospitals that solve this. It won't be patients that solve this. It will be Cerner that solves this. So, what we're seeing here isn't surprising, and it's kind of a natural evolution, in my view, of computing. So we saw this kind of happen in the 1960s, back in the glory days of NASA, where we had computers that cost hundreds of millions of dollars. And if computing costs hundreds of millions of dollars, then most people can't afford it. So as a result, the business model was a few companies that had deep pockets would build large computing centers, and they would sell as a service computing. Sound familiar? So mainframe computing is very similar to cloud computing today, right? Where you essentially have big companies like Amazon that subsidize the investment, the capital investment in large data centers, and then they're able to provide as a service that computing to companies that can't afford to build Amazon-style computing environments. What disrupted that in the 1970s was the integrated chip, basically. So being able to remove vacuum tubes from computers and put ICs into computers meant that you could put essentially a mainframe in a rack and sell it for a couple $100,000. And so this disrupted mainframe computing. And I would argue the same thing is happening today with consumer technologies and mobile devices, giving you the kind of performance and the density of computing in a rack for a couple $100,000. I mean, you can essentially have a cloud computer, we sell them, for $100,000 that does what Amazon does for a few $1 million. And so as the economics begin to make it possible for enterprises to build their own private clouds, then we're going to see a disruption of hyperscale cloud computing. Not to say that mainframe computing didn't persist for decades, it did. And I think public clouds will always be a very important ingredient in innovation because it allows small companies to have the resources of a large internet company with a credit card. But the question is, if you're already a big company and you have many petabytes of data and you intend to grow that, whether you should be held hostage by a particular company's APIs, cost structure, and so forth. And increasingly that is not necessary. OpenStack is enabling this. It's all about economics. Personal computing, just to kind of take you through this kind of a fun history, kind of screwed everything up, right? Because, kind of big computers were designed to run very efficiently as big computers, and then in the 1980s, we saw the personal computers and the architectures of personal computers drive the volume. We used to have hard disks that were the size of this speaker, and then they got smaller and smaller because personal computers were representing the volume in the market, and so we started to see the things that were being manufactured in volume. It was the laptop that brought the price of disks and the form factor of disks down. And the bet that the companies made that put the 5.5-inch, 3.5-inch hard drives, 5.25, 3.5-inch hard drives in the computers was that the volume would make those drives, from a price-performance perspective, cheaper than the smaller volume of dedicated enterprise devices. Internet computing, mobile computing, and as we start to see devices everywhere, I mean, cars, you can't buy a car these days that isn't extremely chatty with some, even if you don't know it. The car's ability to help you in an emergency situation, to broadcast telemetry up, the really innovative companies like Tesla are taking advantage of this to a much greater degree, but you're going to start seeing it from other car companies as well. So we're seeing a new generation of what we'll call hyperscale computing hardware. We're seeing a new generation of, in fact, I'll go back there for a second. That on the right is a Facebook Open Compute data center. And for those of you who are not aware of the Open Compute project, it's open source hardware. So Facebook realized that it was being held back by what HP and Dell wanted to sell them. And the conversation was something like, the server costs this much because it has these features. And Facebook said, well, we don't need these features at the scale we operate, so we're not going to pay for them. And HP and Dell said, you're going to pay for them because this is how we're going to build the servers, because we're not building a special server for you. And they said, okay, then we'll design our own servers and open source the designs. You can build them if you'd like. And when you start to not worry about the reliability of an individual server in your application stack, you don't care about HP's support, HP's warranty, or any of the value that otherwise you might derive from a big expensive HP server that's maybe running VMware, and if it fails, 10 applications go down. It's the exact opposite again, right? That one server is part of a cloud computer which is running one big application, and it doesn't really care if a rack fails or if a server fails. So you start to care a lot less about switches and servers, as individual components of your system in this new paradigm. And so that's just one row in a massive computing facility where Facebook operates. And this facility, which is up in Dalles, Oregon, operates with a PUE of, and you guys do data centers, so you'll appreciate this, 1.02. Most data centers operate with a PUE of 2, which means almost as much power is being spent operating the building and the air conditioning and the kind of other stuff as is spent powering the servers. Facebook spends almost no money on the facility. So they're literally cooling the facility from air that's being drawn through. So it's not really formally an air conditioning system in this building. They've kind of tweaked it so they can use injecting water vapor in, which cools the air, which evaporates before it reaches the servers. There literally was a giant cloud that formed in one of their data centers, and it all exploded once. I mean, this is how much they're pushing, kind of true, actually, crackling and sizzling, and they looked, and there was a giant cloud in the data center, and they'd actually, like, the vapor pressure had changed because of the temperature and gas law stuff. It's important. They changed the way they did some of the power supply stuff so it doesn't, if that happens again, it doesn't all blow up and catch on fire. But I mean, if you look at these racks, they're literally the most bare bones servers you can imagine. And the new ones, the new Open Compute servers have 4 sleds of dual socket Intel CPUs. They have DC power supplies, so they've gone through and they've eliminated all the power supplies because whenever you step voltages down, you lose efficiency. So really trying to recover every aspect of efficiency out of these facilities is the key to Facebook being able to store hundreds of millions of photos, connect 1 billion people, and do what they do without spending what would otherwise be a completely unfathomable amount of money. A new generation of software architectures is emerging. So OpenStack is literally it's an operating system for the data center. It's more of a toolkit for an operating system or a reference implementation, but it allows you to take thousands or tens of thousands of servers and treat them as one system, and to build your application on an abstraction which is based on a nonprofit foundation that you can participate in. And that's the cool thing about OpenStack. So it has support from almost every major IT vendor. And what this means is if you build on top of OpenStack APIs versus, say, Amazon APIs, you can actually participate in the process that defines what they are. And if a company like HP or Cisco or ours or Dell wants to say, hey, we support OpenStack in a public cloud or in a private cloud product, it means interoperability. It means that there is a definition of capabilities which you need to use, or you can't use that trademark. And on the OpenStack board, we're making sure that you're not going to use the OpenStack trademark if you don't provide portability and interoperability and a set of capabilities which matches between these cloud operating systems. You should be able to have an application that can run in multiple Cerner data centers on OpenStack clouds powered by different vendors. And you should be able to buy hardware from anybody you want to buy hardware from as well in this world. So, a new generation of quote-unquote cloud computers is emerging from companies like ours. And we're going to start to see a new generation of software emerge on top of these systems. So you guys are in one of the most exciting fields. I think there's no place where more good can be done for individuals than in this room. And someone's going to win. Someone's going to reinvent medicine. We get to see it from another perspective. We see companies that are producing gene sequencers. We have companies like Genentech that are using cloud computing to reinvent medicine around data. And I think as individuals start collecting more information from things like HealthBook and are able to sequence their genomes and are able to take the habits and the patterns in their daily lives, this will integrate with their healthcare professionals with your software. And I think there's a tremendous opportunity if Cerner embraces cloud computing from any vendor, but OpenStack provides an open and standard and a way to do it which doesn't lock you into any particular vendor. You haven't had that opportunity in 25 years. And I think there's a real opportunity for the next 25 years to be built on the same kind of foundation that the internet companies have built on, which is open source technologies and standards. And standards seem to always win, whether it's TCP/IP, whether it's HTML. If you look at the proprietary ways to do things, in the end, standards win. And thank you all for your time today. It's a real honor to be here, and I look forward to seeing what you create.